Hello everyone. In this lesson, we will continue to study the basic knowledge module. Today, we will learn impulse signals, discuss the definition and properties of impulse couple and unit impulse signal. First, let's discuss unit impulse signals. The content includes the concept, two definitions of the unit impulse signal, the nature of the impulse signal. Some physical phenomena in real life are described by function model with a very short time but an extremely large value, such as the impact force acting instantaneously in mechanics, thunder and lightning in electricity, ideal sampling pulse in digital communication, and so on. The concept of impulse function is from practical problems. So the impulse signal can be defined in different ways. Let's look at the first definition. The impulse function is direct function, well known in mathematics, as shown in Formula 1. Formula 2 is its practical application. Well, how to understand this function? Obviously, when t is equal to 0, the function value is not 0. The area of this function is 1. When t is not equal to 0, the function value is 0. What is the function value when t is equal to 0? Because the integral area is 1, so when t is equal to 0, the function value is approaching infinity. The impulse function is an unbounded function, and it is defined by intensity. As for the second definition, impulse signal is defined according to the generalized function theory. The impulse signal is the limit of the unit rectangular pulse function, as shown in Formula 3, where pt is a unit rectangular pulse. Its area is 1. How to understand this definition? Let's take a look at Figure 2. By comparing Figure 1 and Figure 2, it's clear that the area of pt is 1, and as the pulse width decreases, its pulse height rises. If tau approaches 0, the pulse width is concentrated at t equals 0, and it is approaching infinity. Therefore, the rectangular pulse pt also has three characteristics. The area is 1. When its width approaches 0, its amplitude or height is approaching infinity. Obviously, these three properties and the direct function have the same nature. Therefore, in engineering, when tau approaches 0, we regard the limit of pt as impulse signal. Formula 3 is got according to the generalized function theory. Delta t is the limit of pt. The impulse signal is shown in Figure 3. It is represented by an arrow. In general, one marked beside the arrow represents that this arrow is a unit impulse. That is to say, the intensity of the impulse is 1. In order to show that at this point the function value is approaching infinity, sometimes there is an infinity symbol marked beside the arrow. According to the characteristic of signal shift, delta t minus t0 can be expressed by Figure 4. If the area of the rectangular pulse is k, the intensity of the impulse is also k. In practical engineering, if we take the limit of tau goes to 0, triangular pulse, bilateral exponential pulse, bell-shaped pulse, and the sampling function can be regarded as impulse functions. In order to carry out signal analysis, people constructed the impulse function, which belongs to the generalized function. In terms of time, delta t can be regarded as a continuous signal in the time domain. Because it meets certain rules, of continuous signal operation in the time domain. However, because delta t is a generalized function, it also has some special properties. Here, we will discuss sampling, parity, impulse couple, and scale transformation of the impulse function. First, let's look at sampling. It can also be called screening. If ft is continuous at point where t equals 0 and bounded everywhere, then we got formula 5 and formula 6, and this is the screening of the impulse signal. In formula 5, delta t times ft is equal to f0 times delta 0. You must notice f0 times delta t is still a function. In formula 6, integrating delta t times ft, we can get the value of ft, which is the screening of delta t. In this way, we screen the value of ft. Figure 5 shows the graphical representation of sampling. For the shifted situation, it can be expressed by formula 7. Of course, it can also be expressed by formula 8. In this case, the value of sampled function is ft0. Next, let's move on to parity. According to the definition of delta t is equal to delta minus t, so the impulse function is an even function. When integrating the product of delta quotation t and ft, the result is formula 9. You can prove this formula with partial integral operation. In this expression, ft times delta t is equal to 0 at its negative and positive infinity points. Because when t is not equal to 0, the value of delta t is 0. Using the screening of delta t, we can prove formula 9. Let's study the concept of impulse couple. First, let's look at figure A. Figure A is a triangular pulse. Through calculation, its area is 1. When tau approaches 0, figure A becomes the unit impulse function of figure B. Differentiate the triangular pulse in figure A, we can get S quotation t, as shown in figure C. In figure C, there is a pair of pulses with an area of 1 over tau. One is positive and the other is negative when tau approaches 0. Then figure C becomes figure D. It represents two impulses with infinite strengths. One is positive and the other is negative, which are represented by delta quotation t, and this is the impulse couple. Let's analyze the nature of impulse couple. First, the integral of the product of delta quot t times ft is equal to minus f quot 0, which is formula 10. It can also be regarded as screening of impulse couple. When integrating the product of ft times the k derivative of delta t, we can get formula 11. In formula 11, you should notice minus 1 to the power of k. After time shift, we can get formula 12. Let's take a look at formula 13 and formula 14. This is the integral of negative infinity to positive infinity of delta quot t. It is equal to 0. And formula 14 is the integral from negative infinity to t. It is equal to delta t. When you apply these two formulas, you should notice the difference between them. According to what we mentioned before, formula 15 is proved. In other words, impulse couple is an odd function. Finally, let's look at formula 16 and 17. Formula 16 is the product of ft and impulse couple. Formula 17 is the product of ft and the impulse function. Their results are different. Next, let's take a look at scale transformation of delta t. Delta at is equal to 1 over the absolute value of a times delta t. This is different from scaling of general functions. But what is the scale transformation of impulse couple? By scaling delta quad t, we can get formula 12. It is also different from the scale transformation of general functions. The amplitude value of this function has changed. Similarly, the k derivative of delta t can also be scaled. The result is formula 13. Scale transformation of impulse signal can be proved in this way. From the definition of delta t, we find delta t is the limit of pt. When limiting pt, the result is delta t, and when scaling pt, the graph of pat is on the top right. It is compressed on the time scale, and its amplitude on the vertical axis has not changed. The area of pt is 1. The intensity of delta t is 1. They are same. The area of pat is 1 over the absolute value of a. So the intensity of delta at is 1 over the absolute value of a. So when tau is close to 0, and if pt is approximated to delta t, then pat should force to delta t times 1 over the absolute value of a. Therefore, the scale transformation of delta t are different from the scale transformation of function. Let's summarize the relationship between RT, epsilon t, and delta t. The left figure is the waveform of RT. The middle is the waveform of epsilon t. The right is the waveform of delta t. The derivative of RT is epsilon t. The integral of epsilon t is RT. The derivative of epsilon t is delta t. And the integral of delta t is step signal epsilon t. This is the relationship between them, and this is the mathematical expression of their relationship. Here, you should notice that the integral of delta quad t is equal to 0, and the integral of delta t is 1. That is to say, the integral of impulse couple is 0, and the integral of impulse function is 1. Now, let's summarize the nature of impulse signal and impulse couple signal. First, screening or sampling. Second, parity. The impulse signal is an even function. Third, the scaling on the impulse signal. It is different from the scaling of general functions. Fourth, the property of calculus. This is also the relationship between the step signal and the impulse signal. Next, impulse couple. You should notice that impulse couple is an odd function. In addition, there is another property, convolution. Ft times delta t is equal to Ft. This is another very important property of impulse signal. We will study convolution between the impulse signal and Ft and its related properties in the following module. The content of this lecture is the focus of the difficulty of this course. If you have any questions, you can discuss online. Let's work together to master this knowledge. This class is over. Thank you. Goodbye.